Well, let's start. So my name is Bruno Coitin, and I'm a researcher in University of Namur in Belgium. And my focus today is redistribution communities. And the aim of redistribution communities is to solve a number of drawbacks and limitations of classical BGP communities when they are used to support interdomain traffic engineering techniques. So in order to introduce you redistribution communities, I'll first briefly review what the BGP communities attribute is, then how it is used to support traffic engineering techniques at the interdomain level, then how often it is used. I'll show you the results of an analysis of real BGP tables. Then I'll summarize drawbacks and limitations of these communities used for traffic engineering, and then I'll introduce you our solution, redistribution communities, and then I'll briefly conclude. So first of all, what is this community attribute? Most of you already know that, but I'll briefly review it. So it's simply a list of 32-bit identifiers that can be attached to a route. This is a transitive attribute, meaning that once you have added one identifier to your route, it will remain attached to this route when this route is redistributed, unless a router filters this identifier. What is this community attribute used for? Mainly for two purposes. First of all, to mark routes which share a common property. For instance, ISPs use these communities to mark routes that are coming from a given location. For instance, a geographical location or an interconnection point. The other purpose is to signal that routes must undergo a given treatment, and we'll see more about that in a few slides. What was the intention behind communities? It was to allow network operators to build more scalable and easily maintainable configurations. And yesterday, if you have followed the tutorial by Philip Smith, you have probably heard many times wonderful tools, these communities. Community values can be picked in two different areas. First of all, standardized values that are reserved for well-known meaning, like no export, no advertise, and so on. And another part that can be delegated to each AS. In this case, the community value will be divided in two parts. The first one is the AS number, and the second one is freely allocatable by the AS. We have to note at this point that it is unclear what to do with communities that have an AS number in the private space. We don't know if these communities have to remain local to an AS or if they can be attached to or propagated in the global internet. A classical use of communities is to allow more maintainable configurations in the case of multi-homed or multi-linked networks. For instance, in our very simple topology here, where we have one customer AS10 and one provider AS1, we can use communities to tell AS1 to give specific local preference to routes. For instance, here AS10 would like to do some kind of load balancing over its two links and announce certain prefixes on one link and other prefixes on the other link. The problem with that method is that if one link fails, you lose a part of your reachability. So it's better to announce routes on both links, but ask AS1 to give better preference to routes on their primary link. And to do that, AS10 will attach a community published by AS1 to routes to indicate which preference should be given to these routes. So this was the first use of communities to do some kind of traffic engineering. But today we find new techniques that appear in the global internet. For instance, some AS allow their peers to influence how their routes will be redistributed to other peers. For instance, you can request that your route be not re-announced to specific peers, or that your routes are re-announced with an AS path that has been prepended. And like in RFC 1998, you can also ask to set the local preference. These techniques are very simple and are based on three main steps. First of all, imagine that I am an ISP and I want to allow my peer to influence the way their route will be redistributed. First of all, I will have to configure my routers with policies that will be applied when given community values are attached to routes. Second, I'll have to publish the correspondence between these community values and the actions that will be applied. And then third, my peers will be able to attach such communities to routes, and in order to have given actions applied on their routes. So I'll now give you a few very academic examples in order to clarify things. So in this first example, we will use a community to do selective enhancement. The case here is a case where we have two customers that have a private peering. So on this private peering, AS20 will only announce its own prefixes or the prefixes of its customers. The problem is that AS10 will re-advertise these prefixes to its upstream peers, AS1 and AS2. And so there is a risk that traffic coming from AS1 and AS2 will flow through the private link between AS10 and AS20. That's not what AS20 wants. So the solution will be to use a community attached to routes announced by AS20 to AS10 that will request that AS10 do not re-announce these routes to its upstream peers. Another example where we will request prepending. In this case, we'll take the point of view of AS10, and AS10 sees that it receives a lot of traffic from AS3 and AS4, and would like to achieve a certain kind of load balancing. It would like to shift traffic from AS4 to the link across AS20 and AS30. To do that, it will have to increase artificially the path announced to AS4. This will be done by the way of a community published by AS1 and attached to routes announced to AS1. Here the community will ask that AS1 prepend 2 times when re-announcing to AS4. The result is that the AS path of the route announced to AS4 is prepended 2 times and becomes longer than that the path across AS20 and AS30, and then if no other policies are specified in browsers from AS4, traffic will normally flow through AS20 and AS30. We can see in this case that the AS path of routes announced to AS3 has not been changed. Another observation to do here is that communities attached by AS10 and that have a meaning for AS1 still appears in updates transmitted to AS4 and AS3, while they do not have any meaning for these ASs. So this is due to the transitivity of the community's attribute, and this will cause routing table pollution. So many ISPs often complain that communities are not widely used in the internet. So to be sure of that, we have carried an analysis of real BGP tables collected by RIPE Routing Information Service and by Route Views projects from the University of Oregon. We looked at tables collected during the period from January 2001 to April 2002. And we also had a look at how ASs define the communities and how they publish this information. But I'll show you that in a few slides. So first observation is given in this graph. On the x-axis you have the period of observation, and on the y-axis you have the percentage of routes that have at least one community attached. First observation, the number of communities in routing tables is increasing. You have to know that in a router from route views there are more than 2.5 million routes. You see that at the end of April 2002 there is about 60% of routes that have at least one community attached. So that's 1.5 million routes that have at least one community attached. That's a lot of communities in routing tables. So I think that communities are quite widely used. But this growth of the number of communities is also due to the transitivity of the community attribute. So once communities are attached to routes, they remain attached and are propagated through the global internet, unless they are filtered somewhere. A second observation here, on the y-axis we have the number of different communities found in routing tables. Here also we see that this number is really increasing, and this is again due to the transitivity of the community attribute. Another interesting and somewhat surprising observation was that we found some routes that have many communities attached. Here we have 40 communities attached to a single route, and only one community has a meaning at this place. So there is a lot of pollution here. 39 communities that are useless, with 4 bytes for each community. That's a lot of useless bytes in an update message. So I think that there are many studies about the increasing of the number of prefixes in routing tables and memory and CPU consumption, but I think we should also have a look at communities that are appearing in our routing tables. So a second part of our analysis was to look at how ASs define their community values and how they publish them. So in routing tables we have found different community values, and we took the first part of the communities. So we can find the AS number of the ISP that has published these communities, and then on this basis we have searched for community definitions. We have searched in 2 places. First in Whois databases, where we have found that many ASs define the meaning of the communities in remarks fields in RPSL. But we had also to look at ISP's websites to find the informal definition of community meaning. And with these two sources of information, we had still a lot of ASs for which we couldn't find any community definition. So we guessed that these definitions are exchanged in peering contracts or maybe by email. We don't know. Another short result, the first observation, is the way ASs allow the peers to influence the way that their routes are reannounced. Here we see two actions that are often proposed to peers: prepending and do not announce. And these actions can be targeted in different ways, with an AS number or with a code that specifies an AS or an interconnection point, or also a code that design a set of peers. We'll now have a look at a few examples of community definitions. Here are communities defined by eBone. So we have a value for the do not announce action targeted at different set of peers, like US Upstreams, SprintLink, UUNet, or European peers. Another example with a more elaborate design. Here, Cable and Wireless has decided to propose structured community values by having two fields in their community values. One field design the target, and they have their own peer codes, and the other field specify the action to apply on the route. For instance, to not announce to other peers or to prepend a certain number of times when re-announcing to specified targets. A third example of solution is a solution proposed by Level 3, is to reuse the space that is not allocated to anyone, the space for which it is unsure it can be used or not. We think that this is a selfish behavior, since if every AS use this kind of solution, and we have to keep in mind that the community attribute is transitive, then we can have unpredictable behavior, since ASs can reuse different community values, the same community values, but with different meaning. And these communities will remain attached to routes. So I now summarize a few drawbacks that were identified. First of all, we have seen that in the process of allowing peers to use communities to influence the redistribution of their routes, the description of community values has to be published, but there is no standard method to publish these values and their description. Second, the community attribute has only a limited space. You have only 2 bytes to define your values, and it's not easy with this limited space to define structured values, easy to configure it and to understand. A third drawback is that these techniques require a lot of configurations, of manual configuration. We have seen that you require configuration of policies on the receiving routers and also on sending routers. Moreover, you have to configure different community values for the same kind of actions following the peer on which you want your route to be influenced. And last but not least, the attribute is transitive, and we have seen that this can cause a lot of pollution in routing tables. So we have proposed a solution, and it's currently in discussion at IETF in the P2Main working group. And our solution is based on extended communities. We define a new type of extended communities. The advantage of extended communities is that we can define extended communities that are not transitive, so we avoid the pollution problem. And moreover, the extended communities are 8-byte wide, so we can define structured values. To define structured value, we know that we have to encode two things. First of all, the action to apply to routes. Here we have decided to keep 3 different actions: prepending, attaching the community no export, or do not announce. And we have decided to specify filters in 2 ways: by an AS number or by a CIDR prefix. So to encode this, we only require 7 bytes in the extended communities. The first byte would have to be defined by IANA. So this is not only academic work, this is also pragmatic, and we have tried to prove that this is implementable and that it is easy to implement and that it can be easy to configure. So to do that, we have modified the routing software suite and interface in order to allow network operators to specify action and target. And we have modified the redistribution code of the BGP process of Zebra so that redistribution communities are automatically taken in account and you don't have to do configuration on the receiving router. These modifications were only about 2,000 lines of code. So we think that every router manufacturer could do that. So the process was quite complicated with classical communities. First of all, you had to do a lot of manual configuration on both receiving and sending routers. Now you only have to enable the support of the distribution communities on receiving speaker, and to specify the action and the targets on the sending speaker. I'll now show you 2 examples of what the configuration could be. I use the syntax of a well-known router vendor whose name starts with a C. So here the important part is the statement set X community red standing for redistribution, that we can add in roadmap. You only have here to specify a couple with an action and a target. So here ignore means that the route should not be reannounced, and the target is AS1, so the route will not be reannounced by the receiving router to AS1, and there is a second community attached that specifies that the route should not be reannounced to AS2 as well. Another example here where AS can request that AS1 prepend 2 times when reannouncing to AS4, but this prepending will only be done when reannouncing to AS4 and not to other peers. This is the same kind of configuration. Here the action is prepend 2 times and the target is AS4. So it's easy to do. You don't have to look for the community values used by your peer, and the community values are completely standardized, so everyone uses the same value. So as a conclusion, I'll summarize the advantages of our redistribution communities. We solve all the problem of the classical community attribute. First, with the standardized and structured encoding of our communities, we reduce the risk of misconfiguration and the risk of errors. Moreover, we have devised extended communities that are not sensitive, so we avoid the problem of pollution of BGP tables. And we have shown that these communities are easy to implement and that it can be easy to configure. There are two more applications of our communities. First of all, these communities could be used to reduce the impact of denial of service attacks. We can use these communities in conjunction with tools that can detect such denial of service attack and identify the source of these attacks, and then influence the way our routes are announced towards these sources. A second application would be to use our redistribution communities with route optimization tools, such as tools we will be discussed tomorrow in the panel. Okay, that's it. Thank you for your attention. You can find some reference here if you want to have further information. And if you have any question, I'll be glad to answer it.
Maybe I can start out with the first question.
Yeah.
You had a slide that showed a fair amount of pollution. I was wondering if you could describe, if you know, how that happened, why that happened. Was this just an experiment, folks playing around?
Well, I can return to this slide. So, in fact, communities are added by customer of peers. So that here we can see in the AS path that is the last field on the first line. Yes.
I know why so we did this event, so maybe I can give you an answer. The reason we did that. Sorry. It's better. You know the real reason. You speak? Yeah. So the reason we put such many communities, in fact, is that we wanted that. Sorry, I'm France Telecom, so 5511. The transit has for just this mess. So in fact, the 3561 community was implemented by Open Transit because we wanted that cable do not advertise this prefix to many of his peers. And you see that, as you show in another slide, when we can use the third digit after 30 to say that we don't want to advertise this prefix to many of the cable and wireless peers.
Yeah, that's true.
So in fact, we do not want that this prefix be advertised to Genuity.
Yes. But the problem when we wanted to point out, there was not the big amount of communities to put on route, but the fact that these communities remain attached to the route, even if they have no meaning at the place they are received here.
Yeah, it depends really where you are reading this prefix from. So, but I mean, in the cable and wireless network, it had the added value.
Yes, in fact, each AS that defines such communities should filter these communities before re-announcing route, or should use a solution like Redistribution communities.
Yeah, but between cable and wireless and Open Transit, at this moment, it was not a pairing relation. So we are supposed to use community to traffic engineer our traffic.
But we hope that redistribution communities will be implemented in router
and it should be over. Yeah.
Actually, just one other quick question. In coming up with the three, I think you selected 3 communities, well-known communities.
Yeah.
How many ISPs do you speak with to find that this is a common use of communities?
In fact, this information comes from AS that probably define communities in routing tables from RIBE and road views. So we looked at the community values and we found a certain number of AS numbers, and we tried to find community definition for these ASs.
So entirely by the routing table.
Yeah.
Jim Davis, Agilent. Your slide showing such a huge number of communities points out that your proposal isn't actually needed, since they've managed to encode far more than 8 bytes. A proposal that used the existing communities and defined a multiple community syntax, or sorry, semantics, could have addressed your issue as well, just rather than add one more thing called communities for no good reason. Did you consider defining a semantics for multiple communities to allow you to get...
Yes, in fact, you can attach more than one redistribution community to a route to have more to have many actions applied to your route.
Or using existing communities,
No,
if there was a defined value that said don't redistribute, and if you used multiple communities to represent the semantics that you wanted, you could have done it without changing, for
Yes,
example, any router manufacturer's command syntax.
Even if we were reusing the classical community attribute, we have to find a space that we can reuse, and it's not sure that we can do that. And moreover, the space is really limited. So with 2 bytes, we find that this is too short to do what we want. For instance, to specify targets in the form of a CIDR prefix, that's not possible with simple community attribute. I hope that answers your question.
Well, great. Thanks a lot.